Hello and welcome. This is the Science Channel for Sleep. If this is your first time here, you have found a quiet corner of the internet, a place designed for rest, for gentle learning, and for letting the mind settle into something calm and unhurried as sleep approaches. And if you have been here before, it is always good to have you back. Take a moment right now to settle in. Adjust your pillow, pull your blanket a little closer, and let your body relax into wherever you are resting tonight. There is nothing you need to do in this hour except listen. Whatever filled your day, the decisions, the noise, the tasks that seemed urgent this morning, all of it can wait until morning. This time belongs entirely to you. Before we begin, if you enjoy this kind of calm, educational content, a like and a subscription are always appreciated. They help other people who are looking for exactly this kind of quiet place to wind down find their way here. And if you have already subscribed, thank you sincerely for being part of this community. Now, where are you tonight? What time is it there, wherever you are listening from? Are you somewhere in the early evening, the day not quite finished outside your window? Or is it late, the house quiet, the world beyond your walls dark and still? It is always interesting discovering where listeners are tuning in from around the world. Some of you may be in cities where the night sky glows with artificial light. Others may be in places where the stars are sharp and the darkness is complete. And some of you, perhaps a few, may be in high northern latitudes where, if conditions are right, you might step outside tonight and see the very thing we are going to spend this hour exploring together. Tonight, we are going to talk about the northern lights, the aurora borealis. The phrase itself carries something ancient in it. Aurora from the Roman goddess of dawn, borealis from Boreas, the Greek god of the north wind. Together, they give a name to one of the most quietly extraordinary natural phenomena visible from the surface of our planet. A light that appears in the dark sky without fire, without any obvious source, shifting and folding and dissolving across the polar night above anyone fortunate enough to be in the right place at the right time. In the southern hemisphere, the same phenomenon occurs simultaneously. The aurora australis, the southern lights, an almost perfect mirror of the northern display, visible from Antarctica, the southern tip of South America, and occasionally from parts of New Zealand and Tasmania during the most powerful events. Both are caused by the same fundamental process. Charged particles streaming outward from the sun travel millions of kilometers through space, encounter the protective magnetic field that surrounds our planet, and some of them, channeled by that field toward the poles, descend into the upper atmosphere. There, they collide with atoms of oxygen and nitrogen. Those atoms absorb the energy of the collision and then release it as light. That light, drifting and rippling above the polar regions, is what people have looked up at and wondered about for as long as human beings have lived in the high latitudes of this world. Tonight, we will explore all of it. The sun, the solar wind, the magnetic field, the atoms, the colors, the history, the mythology, and the quiet experience of standing beneath a dark sky and watching the lights move. Let your eyes close, if they are ready. To understand the northern lights, we need to begin not at Earth, but at the sun, 150 million kilometers away. That distance is vast by everyday standards. Light itself takes about 8 minutes to cross it. And yet, the sun's influence reaches us continuously, not just as light and warmth, but as something more physical. A constant outward flow of charged particles that streams in every direction from the sun's surface and its outer atmosphere, filling the solar system with what researchers sometimes describe as a kind of perpetual breath. This flow is called the solar wind. It consists primarily of electrons and protons, the fundamental charged particles of atomic matter, released from the sun in enormous quantities every second and propelled outward at speeds ranging from approximately 400 to 800 kilometers per second. At those speeds, the particles take roughly 1 to 4 days to travel from the sun to Earth. By the time they arrive, they carry with them not just their own kinetic energy, but something else of great importance: a magnetic field from the sun itself. The sun has its own powerful magnetic field, and as the solar wind flows outward, it carries that field with it, stretching and distorting it throughout the solar system. Scientists call this the interplanetary magnetic field. It is not a simple, uniform structure. It varies in strength and direction continuously as the solar wind itself varies. And as we will explore in the next section, the direction of this interplanetary magnetic field when it arrives at Earth is one of the most critical factors in determining how active the aurora will be on any given night. It is the difference between a quiet, dim arc barely visible at the horizon and a full, dynamic display filling the sky with rippling green and red. The solar wind is not a steady, uniform stream. It varies enormously in speed, density, and energy from hour to hour and day to day. On quieter days, the flow is relatively gentle, producing modest aurora activity, confined to the highest latitudes. But the sun is a dynamic, active star, and it periodically produces events that send far more intense surges of particles and energy toward Earth. Solar flares are one such event. A solar flare is a sudden, intense release of energy from a region of the sun's surface where the magnetic field has become twisted and complex. A flare can produce bursts of X-rays that travel at the speed of light, arriving at Earth in 8 minutes, and also accelerated particles traveling at velocities much higher than the ordinary solar wind. When these particle bursts arrive, they can trigger heightened aurora activity. The effects on Earth's magnetic environment can begin within an hour of the flare's occurrence on the sun. Coronal mass ejections, known as CMEs, are a related but distinct phenomenon. A CME is a large eruption of magnetized plasma from the sun's outer atmosphere, the corona, a vast bubble of charged particles, an embedded magnetic field, launched into the solar system at speeds ranging from a few hundred to several thousand kilometers per second. CMEs are slower than the X-rays and energetic particles from a solar flare. They typically take 1 to 3 days to reach Earth. But when a CME arrives and collides with Earth's magnetic field, the consequences can be significant. CME impacts can trigger geomagnetic storms, periods of sustained and intensified aurora activity that can last for hours to days and can bring aurora displays to latitudes far south of the polar regions where the lights are normally seen. The frequency of both solar flares and CMEs follows a predictable rhythm. The sun goes through an approximately 11-year cycle of increasing and then decreasing magnetic activity. From solar maximum, when the sun is most active and produces the most flares and CMEs, to solar minimum, when activity quiets considerably. During solar maximum years, aurora events are more frequent, more intense, and visible at lower latitudes than during the quieter years of solar minimum. During minimum, aurora is less frequent and generally confined to the very highest latitudes. Interestingly, the most recent solar maximum occurred approximately in 2024 and 2025, making these particular years unusually active ones for aurora viewing across the globe. People living well south of the typical aurora zone have reported seeing the lights during this period, sometimes from locations where aurora had not been seen in decades. This heightened activity is a direct consequence of increased solar energy output during this phase of the cycle. Humanity has placed a sentinel in space specifically to monitor the solar wind before it arrives at Earth. The DSCO-VR satellite sits at a point called the L1 Lagrange point, approximately 1.5 million kilometers from Earth in the direction of the Sun, where the gravitational pull of Earth and Sun balance each other, allowing a spacecraft to remain in a relatively stable position between the two. From this vantage point, DSCO-VR continuously measures the solar wind speed, density, temperature, and crucially, the direction of the interplanetary magnetic field. When conditions change in ways that suggest aurora activity is about to intensify, this data reaches Earth approximately 15 to 60 minutes before the solar wind itself arrives. A brief but genuinely valuable early warning for space weather forecasters and aurora enthusiasts alike. It is a quiet thing to consider. The electrons that will produce tonight's aurora, somewhere above the Arctic right now, began their journey at the Sun. They traveled millions of kilometers through the cold, empty expanse of interplanetary space, crossing a distance that is almost beyond everyday comprehension, carrying their energy patiently across the solar system. And at the end of that journey, their energy will be converted into something visible and gentle, soft light shifting in the polar sky, visible to anyone standing outside in the cold and looking up. Earth is not unprotected against the solar wind. Between the surface of our planet and the constant outward flow of charged particles streaming from the Sun stands an invisible but remarkably effective barrier: the magnetosphere. This is Earth's magnetic field extended into space, forming a vast protective bubble that deflects the great majority of the solar wind around the planet, rather than allowing it to strike the surface and upper atmosphere directly. Without this shield, the consequences for life on Earth would be significant. The magnetosphere is, in a quiet and fundamental sense, one of the reasons life as we know it has been able to persist on this planet for billions of years. The magnetosphere is not a simple sphere. Its shape is continuously distorted by the pressure of the solar wind pressing against it from the sunward side. On the side facing the Sun, the magnetosphere is compressed inward, pushed to a distance of roughly 10 Earth radii, or about 64,000 kilometers from Earth's center. On the opposite side, the night side, the solar wind stretches the magnetic field out into a long, tapering structure called the magnetotail, which extends hundreds of thousands of kilometers behind Earth. reaching far beyond the orbit of the Moon. This elongated night-side structure plays a central and crucial role in the production of aurora, as it is here that the energy driving most aurora displays is stored and eventually released. For most of the solar wind's particles, the magnetosphere works exactly as designed, deflecting the flow smoothly around the planet, protecting the surface from direct particle bombardment. Researchers believe that without this protection, the solar wind would gradually strip away Earth's atmosphere over geological timescales, much as it has done to Mars, which lacks a significant global magnetic field and has lost most of its ancient atmosphere as a consequence. The aurora is, in this sense, a visible reminder that the protective system is active. The glow at the entry points, where the magnetosphere's influence is most directly engaged with the incoming solar wind. The critical factor that determines how much solar wind energy enters the magnetosphere on any given day is the direction of the interplanetary magnetic field. The magnetic field carried by the solar wind outward from the Sun. Earth's own magnetic field on the sunward side points generally northward. When the solar wind's magnetic field also points northward, the two fields are aligned in the same direction. Aligned fields repel rather than connect. The magnetosphere remains relatively well sealed against the solar wind, and aurora activity stays modest. But when the interplanetary magnetic field points southward, opposite to Earth's northward pointing dayside field, something fundamentally different happens. The two opposing magnetic fields can interact through a process called magnetic reconnection. In reconnection, magnetic field lines that are pointing in opposite directions break and reconnect with each other across the boundary, joining what were separate field systems into a new, connected configuration. This process allows solar wind energy and particles to flow through the newly connected field lines into the magnetosphere, opening, in effect, a temporary door in the protective bubble through which the solar wind's energy can enter. The energy that flows in through this door does not immediately produce aurora. Instead, much of it is transported around the outer magnetosphere and accumulated in the stretched magnetic field of the magnetotail on the night side. The magnetotail in this state is like a compressed spring, storing magnetic energy as the field lines are progressively stretched and loaded by the ongoing solar wind interaction. Eventually, when the stored energy reaches a critical threshold, a reconnection event occurs within the magnetotail itself. The spring releases its stored energy suddenly, a process called a substorm, accelerating electrons powerfully along magnetic field lines that converge toward the polar upper atmosphere. These accelerated electrons travel along the magnetic field lines from the distant magnetotail toward the poles at extraordinary speeds. Researchers have measured aurora-producing electrons traveling at approximately 70 kilometers per second. Following the field lines like beads on an invisible wire, they are guided from the outer regions of the magnetosphere all the way down to the polar upper atmosphere. There, where Earth's magnetic field lines converge and dip toward the surface at steep angles, the electrons enter the dense enough air of the thermosphere and begin the collisions that produce aurora light. The electrical connection between the outer magnetosphere and the upper atmosphere is maintained by structures called Birkeland currents, sheets of electrical current flowing along the magnetic field lines between the magnetosphere and the polar ionosphere. These currents are named after the Norwegian scientist Christian Birkeland, who proposed their existence in the early 20th century, long before the technology existed to confirm them. During a geomagnetic storm, the total electrical current flowing in the auroral zone through these structures can reach 1 million amperes or more, an enormous flow of electrical energy through the upper atmosphere, invisible from the ground, but measurable by sensitive instruments. One reason the magnetosphere is so remarkable is its dual nature. It is Earth's primary defense against the solar wind, deflecting the harmful particle radiation that would otherwise reach the surface. And simultaneously, it is the structure that enables the aurora, concentrating and channeling the small fraction of solar wind energy that does enter, directing it toward the poles where it can produce one of the most beautiful natural phenomena on our planet. The same system that protects Earth produces the northern lights. Protection and beauty arise from the same invisible architecture of magnetic force surrounding our world. Earth's magnetic field is unfelt and unseen in daily life. We navigate by its influence through compass needles and GPS satellites, but we do not directly perceive it. In the polar sky, when conditions are right, it becomes visible, traced in shifting curtains of light by the electrons following its lines of force down into the atmosphere. The aurora is, in a quiet and literal sense, Earth's magnetic field made luminous. When the energized electrons, guided by Earth's magnetic field, arrive in the upper atmosphere, they enter a region of increasingly dense gas, the thermosphere, where atoms and molecules of oxygen and nitrogen are present in sufficient quantities for collisions to become frequent. It is in these collisions, happening continuously across the vast thin shell of the upper atmosphere above the polar regions, that the aurora's light is born. The process is governed by some of the most fundamental principles of atomic physics, and understanding it reveals something genuinely beautiful about the relationship between energy, matter, and light. The electrons arrive with kinetic energy of motion acquired during their acceleration through the magnetosphere. When one of these energized electrons collides with an atom of oxygen or a molecule of nitrogen in the upper atmosphere, it transfers some of its energy to that atom. This transferred energy does something specific and well understood. It displaces one of the atom's own electrons to a higher energy level, farther from the nucleus than its normal resting position. Physicists describe this state as excitation. The atom has absorbed energy and is now in an elevated, temporarily unstable configuration. This excited state does not persist indefinitely. After a period that varies by atom and energy level, ranging from fractions of a second to several minutes, the displaced electron falls back down to its normal, lower energy level. In doing so, the energy that was absorbed during the collision must be released. It cannot simply disappear. The conservation of energy is one of the most fundamental laws of physics. Instead, the energy is emitted as a photon of light. The wavelength of that photon, which determines its color as perceived by the human eye, depends precisely on the difference in energy between the excited state and the ground state. Different atoms and molecules have different energy level structures. So they emit photons of different wavelengths, which means different colors. This process, an electron in an atom absorbing energy, jumping to a higher level, and then emitting light as it returns to the ground state, is called atomic emission. It is the same fundamental mechanism that produces the characteristic colors of neon signs, the specific glow of fluorescent lights, the colors of fireworks in the sky, and the spectral lines that astronomers use to identify the chemical composition of distant stars. In the aurora, the energy that drives the process arrives not from an electrical power outlet or an explosive chemical reaction, but from electrons streaming down from the magnetosphere, themselves energized by the interaction of Earth's magnetic field with the solar wind. The green color that most people associate most strongly with the northern lights is produced by oxygen atoms at altitudes of approximately 100 to 150 kilometers. At these altitudes, the atmosphere is thin enough for the aurora to be visible, but dense enough for collisions to occur frequently. Excited oxygen at these altitudes emits green light with a characteristic wavelength of approximately 557 nanometers, a vivid, clear green that the human eye is particularly sensitive to. This is one reason green is the dominant color in most aurora displays. The eye perceives it well, and it is produced at the altitude where particle precipitation is most concentrated. Red aurora is produced by the same oxygen atom, but at higher altitudes, typically above approximately 200 kilometers, where the atmosphere is considerably thinner. At these altitudes, collisions between atoms are much less frequent, and this matters for the color produced because the excited oxygen state that produces red light has a longer lifetime than the one that produces green. The electron can remain in the excited state for up to approximately 2 minutes before emitting its photon. At lower altitudes, where collisions are frequent, a second collision typically de-excites the atom before it has time to emit red light. The energy is lost as heat rather than light. But at the thinner, higher altitudes, the atom has enough time undisturbed to complete the emission and release red light. This is why red aurora tends to appear at the tops of aurora displays, where the highest altitudes are reached, with green appearing at the lower, denser boundary. Blue and purple aurora colors are produced by nitrogen molecules, predominantly at altitudes below approximately 100 kilometers, where nitrogen is more abundant and particle precipitation is intense enough to reach the denser, lower atmosphere. Nitrogen emits more rapidly than oxygen. Its excited states have shorter lifetimes, and the blue and violet wavelengths it produces appear at the lowest visible edges of aurora displays. When red oxygen emission at high altitude and blue nitrogen emission at lower altitude overlap in the same part of the sky, the eye sees the mixture as pink or magenta, colors that appear around the lower fringes of tall aurora displays and give some of the most vivid aurora events their distinctive pinkish edges. White aurora occurs when multiple color emissions are mixed in approximately equal proportions, and the eye, which processes color through its cone cells, perceives the combination as white rather than any single hue. This tends to occur in the brightest and most active aurora displays, where the emission is intense enough across multiple wavelengths simultaneously. One reason aurora photography looks different from the direct visual experience is precisely this cellular biology of perception. The human eye's color-sensitive cone cells require a certain minimum light level to activate. In dim aurora, only the rod cells, which detect light intensity but not color, are sufficiently stimulated. The aurora appears gray or white, even though a camera with a longer exposure reveals brilliant green. As the aurora brightens, the cones begin to activate, and the colors become visible to the naked eye. The brightest aurora events can show vivid greens, reds, and blues visually, matching what cameras capture. Every color in the northern lights corresponds to a specific atom at a specific altitude, releasing a specific amount of energy as a specific wavelength of light. The diversity of what appears in the sky as a shifting, colorful display is the visible expression of atomic physics operating at the scale of the entire polar upper atmosphere. The aurora does not simply appear as a uniform glow spread evenly across the polar sky. It takes specific forms, recognizable structures shaped by the geometry of Earth's magnetic field, the distribution of incoming particles, and the dynamics of the magnetosphere above. These forms change over the course of an aurora event, progressing through a sequence that reflects the evolving energy release happening hundreds of kilometers above the observer's head. Understanding the shapes of the aurora and the way they move adds a layer of meaning to something that might otherwise appear simply as beautiful and inexplicable light. The most common and most familiar aurora form is the arc. An aurora arc is a curved band of light stretching across the sky from one horizon toward the other, oriented roughly east to west and following the curvature of Earth's magnetic field lines as they lie across the sky. Arcs are typically the first form to appear at the beginning of an aurora event. A quiet, relatively steady band of pale green or white light sitting above the northern horizon, bright enough to be clearly visible, but moving slowly, if at all. For observers unfamiliar with aurora, a modest arc can sometimes be mistaken for distant clouds or a lingering twilight. But its position, its color, and its steadiness distinguish it from anything meteorological. From the arc, as the aurora event develops and the energy input from the magnetosphere increases, more complex structures emerge. Rays are one of the first embellishments, vertical streaks of light extending upward from the arc, parallel to the direction of the local magnetic field lines. These rays give a sense of height and depth to the display, suggesting the enormous vertical extent of the aurora column, reaching upward from the base of the emission to far above. When the rays become more numerous and the arc begins to fold and ripple in 3 dimensions, the structure becomes what observers and scientists call a curtain, a sheet-like formation that undulates and folds like fabric caught in a breeze. Aurora curtains are among the most visually captivating forms the lights can take. They move, they fold, they brighten and dim in waves that travel along their length at speeds that, while visually graceful and slow-seeming, actually correspond to motions of tens of kilometers per second in the underlying particle distribution. The folding of aurora curtains reflects small-scale structures in the distribution of particle precipitation, variations in the intensity and position of the incoming electron streams that produce the light. If the observer is fortunate enough to be directly beneath the most active part of a display, they may witness the corona form, one of the most visually immersive aurora experiences possible. In a corona display, rays extend from all directions around the horizon and converge toward a single bright point directly overhead, along the direction of the local magnetic field lines. Standing beneath a corona is like being at the center of a dome of light, rays radiating outward from the zenith in every direction, the entire sky seemingly organized around the point directly above the observer. It is a perspective on the aurora that makes immediately clear the three-dimensional structure of the phenomenon. The observer standing at the bottom of a vast column of light extending upward into space. Diffuse aurora is a less structured form, a broad, relatively uniform glow spread across portions of the sky without the sharp edges and complex patterns of arcs, curtains, and rays. Diffuse aurora often appears at the beginning and the end of aurora events, when the particle precipitation is spread more evenly across the auroral zone rather than concentrated in narrow sheets. It is also frequently the dominant form after a substorm's active phase has passed and the display is subsiding into its recovery phase. Pulsating aurora is a distinct and fascinating phenomenon. Patches of aurora that flicker on and off at regular intervals, typically with periods of a few seconds. Pulsating aurora is caused by wave-particle interactions in the magnetosphere. Electromagnetic waves within the magnetospheric plasma that periodically accelerate electrons and cause them to precipitate into the atmosphere in bursts. The resulting aurora flickers rhythmically, often covering large areas of the sky in a gentle, coordinated pulsing that has a quality quite different from the flowing, dynamic movement of curtain aurora. A typical aurora substorm event follows a recognizable progression. It begins with relatively quiet, steady arcs at the poleward horizon. As the energy release in the magnetotail intensifies, the arcs brighten and begin to move poleward. Then comes the breakup phase, a sudden and dramatic increase in brightness and activity, with rays and curtains forming rapidly, colors intensifying, and the display expanding to cover much of the sky. This breakup phase is the most visually spectacular part of most aurora events. It subsides after roughly 30 minutes to an hour into the recovery phase, a gradual dimming and restructuring back toward diffuse glows and quiet arcs. The entire cycle, from onset to recovery, typically spans 1 to 3 hours. During a major geomagnetic storm, multiple substorm cycles can follow each other in sequence, producing repeated intensifications over many hours. The altitude range of the aurora adds another dimension to its structure. The lower boundary of visible aurora emission occurs at approximately 80 to 100 kilometers, the altitude at which the atmosphere becomes dense enough for particle collisions to produce visible light efficiently. The upper boundary of the main emission region is typically around 200 to 300 kilometers, though during intense events, aurora emission can extend to 500 kilometers or above. The green layer tends to form lower, the red layer higher, and the overall vertical extent of a curtain display can be measured in hundreds of kilometers, though it appears as a relatively thin sheet from the ground because it is observed nearly edge-on. The KP index, ranging from 0 to 9, is the primary tool used to quantify geomagnetic activity and forecast aurora visibility. It is calculated every 3 hours from magnetometer readings at 13 stations distributed around the world, capturing the global level of geomagnetic disturbance. At a KP of 5 or higher, a geomagnetic storm is underway, and aurora begins to be visible at lower latitudes. At KP 9, the maximum, aurora can be seen across the continental United States and deep into Central Europe. The northern lights do not appear randomly across the sky of the northern hemisphere. They are concentrated in a specific geographic zone, a ring-shaped region that encircles Earth's magnetic pole like a luminous crown, shifting and expanding with the level of solar activity, but always returning to roughly the same band of latitude when conditions are quiet. This ring is called the auroral oval, and understanding it is essential for understanding both where the aurora can be seen and why it appears where it does, rather than somewhere else. The auroral oval is centered not on Earth's geographic North Pole, the point around which Earth rotates, but on Earth's magnetic North Pole, which is a distinct and separate location. The magnetic North Pole is currently situated in the Canadian Arctic, displaced from the geographic pole by roughly 15 to 20 degrees of latitude. It is also not stationary. Earth's magnetic pole drifts slowly over time, and in recent decades, it has been moving at a rate of approximately 50 kilometers per year in the direction of Siberia, a migration that has gradually shifted the auroral oval's position. The oval follows the magnetic pole, not the geographic one, because the aurora is a magnetic phenomenon. The particles producing it are guided by magnetic field lines, not by the planet's rotational geometry. Under quiet geomagnetic conditions, when solar activity is modest and the solar wind is relatively calm, the auroral oval in the northern hemisphere typically lies at latitudes between approximately 65 and 72 degrees north. This places it over some of the most sparsely populated regions of Earth: the northern coasts of Norway, Iceland, Greenland, Canada, and Alaska, and parts of northern Russia and Siberia. Within this zone, auroras are a routine occurrence, visible on many clear nights throughout the autumn, winter, and spring months, ranging from faint arcs barely visible above the horizon to brilliant full-sky displays depending on the level of solar activity. The locations most celebrated for aurora viewing lie within or just equatorward of this quiet time oval. Tromsø in northern Norway, at approximately 70 degrees north, is one of the best positioned inhabited cities in the world for aurora observation. Iceland, particularly its northern regions, sits directly under the oval during many active periods. Northern Finland, the region known as Finnish Lapland, has become one of the most popular aurora tourism destinations in the world, offering dark skies, relatively accessible infrastructure, and an almost guaranteed aurora season from September through March. In North America, the Yukon and Northwest Territories of Canada, as well as Alaska, provide similarly excellent positioning, with the added attraction of vast, dark wilderness landscapes under the lights. What makes an ideal aurora viewing night extends beyond simply being at the right latitude. The sky must be clear of cloud cover. The most common reason that planned aurora viewing is unsuccessful even during active geomagnetic conditions. Artificial light pollution reduces the contrast of the aurora against the sky, so locations away from cities provide dramatically better viewing. The time of night matters as well. Aurora activity often peaks around local magnetic midnight, when the observer's location is on the side of Earth most directly connected to the night-side magnetosphere, where aurora energy is released. And the moon can act like a form of natural light pollution. A bright full moon reduces the visibility of faint aurora much as a street light does. Seasonally, aurora occurs year-round wherever geomagnetic conditions are appropriate, but it cannot be seen during the extended daylight of the Arctic summer, when the sky never fully darkens. Autumn and spring. From roughly September through early November, and from late January through March in the Northern Hemisphere, provide the best combination of long, dark nights and temperatures that are cold but not extreme enough to make outdoor aurora watching uncomfortable. Researchers have also noted a subtle but consistent pattern of slightly enhanced aurora activity around the equinoxes, a phenomenon sometimes called the Russell-McFerran effect, attributed to the favorable geometry between Earth's magnetic field and the solar wind during equinox periods. During geomagnetic storms, triggered by CME impacts or other solar events, the auroral oval expands significantly toward lower latitudes. At a KP index of 5, aurora may be visible from the northern United States and southern Canada, states and provinces that might see aurora only a handful of times per decade under normal conditions. At KP 7 or 8, the oval can expand to bring aurora into Central Europe, the northern British Isles, and the northern tier of American states. At the maximum KP of 9, representing an extreme geomagnetic storm, aurora has been observed as far south as Florida, Texas, the Mediterranean coast of Europe, and parts of the American Southwest. During these rare events, people across a wide band of latitude step outside to a sky they may never have seen before and may never see again for many years. Modern technology has made aurora viewing considerably more accessible and predictable than at any previous point in history. Smartphone applications connected to real-time space weather data streams provide current KP readings, forecasts for the next few hours, and alerts when activity reaches levels likely to produce visible aurora at the user's location. Websites operated by space weather agencies provide continuous updates on solar wind conditions and geomagnetic activity. Webcams in popular aurora destinations in Norway, Iceland, and Canada broadcast live views of the sky, allowing people worldwide to watch aurora events as they unfold. The combination of these tools has transformed aurora watching from an activity dependent on local knowledge and good fortune into something that can be planned and anticipated with reasonable accuracy. The aurora is beautiful from the ground. Seen from a hillside in northern Norway or the shore of an Icelandic fjord, it is one of the most serene and quietly moving experiences available in the natural world. But the space weather events that produce the aurora are not peaceful at the scale of the magnetosphere. They involve the rapid release of enormous quantities of energy, the acceleration of particles to extraordinary velocities, and the transmission of powerful electrical currents through Earth's upper atmosphere and, indirectly, through the technological infrastructure of modern civilization at ground level. Understanding the aurora means understanding these events and what they can mean for the world we have built. The fundamental unit of aurora energy release is the substorm. A substorm is a relatively localized eruption of energy within the magnetosphere, triggered by magnetic reconnection in the magnetotail, in which the magnetic energy that has been stored in the stretched night-side magnetic field is suddenly released. A single substorm typically lasts 1 to 3 hours from onset to recovery. The energy released in a major substorm has been estimated to be comparable to that of a magnitude 5 or 6 earthquake, not in the form of ground-shaking seismic waves, but as electromagnetic and particle energy distributed across the upper atmosphere of the polar regions. From the ground, this energy release is visible as the dramatic breakup phase of an aurora display. The sudden brightening, the rapid movement, the curtains and rays expanding across the sky. When a CME from the Sun arrives at Earth's magnetosphere, it does not typically trigger just one substorm. Instead, the sustained compression and energy injection from the CME impact can drive a sequence of substorms over many hours, each one producing a new intensification of the aurora display, a new burst of movement and brightness that rises and fades before the next one begins. This sustained activity is what scientists call a geomagnetic storm, a period of elevated and prolonged geomagnetic disturbance driven by the ongoing interaction between the CME's magnetic field and Earth's magnetosphere. Geomagnetic storms are classified on the G scale from G1, representing minor disturbances, to G5, representing extreme events. The most powerful geomagnetic storm ever recorded occurred in September 1859. It is known as the Carrington event, named after British astronomer Richard Carrington, who on September 1st of that year observed an extraordinarily bright flare on the Sun. A sudden, intense brightening of a region of the solar surface that lasted only a few minutes. Carrington recognized what he was seeing as something unusual and recorded it carefully. About 17 hours later, much faster than a typical CME, an enormous cloud of magnetized plasma struck Earth's magnetosphere. The resulting geomagnetic storm was of a magnitude that has not been equaled in the recorded instrumental era since. The Carrington event produced aurora visible around the world, at latitudes far south of anything normally associated with the Northern Lights. Aurora was reported from Cuba, the Bahamas, Jamaica, and parts of Colombia and Venezuela. In the Rocky Mountains, gold miners woke up in the middle of the night, believing it was dawn because the aurora was so bright. In the northeastern United States and across Europe, telegraph networks, the most advanced electrical technology of the time, were overwhelmed by the geomagnetically induced electrical currents flowing through their wires. Telegraph operators received electrical shocks from their equipment. Some telegraph stations that had been disconnected from their batteries found their systems still operating, powered by the currents induced directly in their wires by the changing magnetic field. It was, for the technology of 1859, both a wonder and a disruption. What the Carrington event implies for the modern world is a matter of serious ongoing study. In 1859, the entire electrical infrastructure of human civilization consisted of telegraph lines. Today, That infrastructure encompasses global power grids with millions of kilometers of high-voltage transmission lines, thousands of satellites in low Earth orbit, GPS navigation systems, cellular and internet communications networks, and a vast array of electronic systems embedded in nearly every aspect of daily life. A geomagnetic storm of Carrington magnitude striking today would interact with all of it simultaneously. Studies conducted by the National Academy of Sciences and other research bodies have estimated that damage from a Carrington-scale event could reach into the trillions of dollars, with recovery periods of months to years for the most severely affected regions of the power grid. A more recent and instructive example occurred in March 1989, when a significant geomagnetic storm, classified at the G5 extreme level, struck Earth's magnetosphere. In the Canadian province of Quebec, geomagnetically induced currents flowing through the Hydro-Quebec power transmission system caused a cascading failure of protective relays. The entire provincial power grid collapsed in approximately 90 seconds. 6 million people lost electrical power for up to 9 hours. Aluminum smelters lost their power mid-process, causing significant equipment damage. Across the northeastern United States, several power transformers were damaged. The aurora associated with this storm was visible as far south as Florida and Texas, a spectacle for observers outside, even as the electrical infrastructure of a major industrial region failed beneath the same lights. The practical consequences of aurora driving space weather extend beyond power grids. Satellites in low Earth orbit are affected because the heating of the upper atmosphere by aurora particle precipitation causes the thermosphere to expand outward, increasing the atmospheric drag experienced by satellites at altitudes of a few hundred kilometers. This increased drag causes orbital decay to accelerate. Satellites descend toward Earth faster than planned, requiring more frequent orbit-raising maneuvers and shortening their operational lifetimes. GPS satellites are affected in a different way. The irregularities introduced into the ionosphere by aurora activity cause GPS signals to be refracted unpredictably, introducing positioning errors that can reach tens of meters during strong events. Airlines operating transoceanic routes rely on high-frequency radio communications that use the ionosphere as a reflector. During aurora events, the ionosphere can absorb rather than reflect these signals, producing complete radio blackouts and forcing aircraft to reroute or use alternative communications. Space weather forecasting has emerged as an important applied science in response to these vulnerabilities. The NOAA Space Weather Prediction Center issues alerts and forecasts for geomagnetic storms on the G-scale, similar in concept to severe weather warnings issued for terrestrial storms. Power grid operators, satellite operators, and airline dispatchers use these forecasts to take protective measures, adjusting grid configurations, changing satellite operations modes, and rerouting flights away from polar regions where radio blackouts are most severe. The northern lights have been part of human experience for as long as human beings have lived at high latitudes, which is to say, for tens of thousands of years, long before anyone understood what caused them. People looked up at the shifting lights in the dark sky and did what human beings do when confronted with something beautiful and unexplained. They recorded it, They described it, they wondered about it, and they tried to make sense of it in the context of their existing understanding of the world. The result is a history of aurora observation that stretches from the earliest written records of ancient civilizations through the careful scientific work of the past 3 centuries. A history that is both a story of human curiosity and a record of how the scientific understanding of a natural phenomenon can grow from simple observation to deep explanation over time. The earliest possible written reference to the aurora appears in Chinese astronomical texts, where records that may describe aurora displays have been dated to as early as 2600 BCE, more than 4,500 years ago. Whether these ancient Chinese observations were indeed of the aurora cannot be established with certainty, but the descriptions of unusual lights in the northern sky have been interpreted by historians of astronomy as consistent with major aurora events visible at the latitudes of ancient China during periods of elevated solar activity. In the Western classical tradition, the Greek philosopher Aristotle described unusual atmospheric phenomena in his work Meteorologica, written around 340 BCE, that may have included aurora observations. He referred to phenomena that appeared as flames, chasms, and burning clouds in the sky. Descriptions that, allowing for the interpretive vocabulary of ancient natural philosophy, are consistent with the appearance of aurora displays. The Roman historian Julius Caesar reportedly described a reddish glow visible on the northern horizon as his troops prepared military operations near the Rhine River, an observation that has been interpreted as a possible low-latitude aurora associated with a period of intense solar activity. One of the most extensively documented historical aurora events occurred in 1770, when an exceptionally bright aurora was visible across an unusually wide range of latitudes, including Japan, where it was observed and described in considerable detail. Japanese observers, for whom aurora was a largely unfamiliar phenomenon at their latitude, recorded their observations carefully, and their accounts provide one of the most vivid historical descriptions of a major geomagnetic storm's aurora display visible far south of the polar regions. The first significant scientific step toward understanding the aurora was taken by Edmund Halley, the British astronomer best known today for the comet that bears his name, who in 1716 made careful observations of a bright aurora visible across much of England and proposed that the lights were related to magnetic phenomena. Halley had noticed that the structure of the aurora seemed to align with compass directions, and he suggested that the lights might be produced by some kind of luminous material flowing along the lines of Earth's magnetic field. This was a remarkable insight for the time, the first serious scientific proposal connecting the aurora to Earth's magnetism. In 1741, the Swedish scientist Anders Celsius, whose name we now associate with the temperature scale he developed, and his colleague Olof Hjorter made a more direct and quantitative connection. They observed that the positions of compass needles in their laboratory were disturbed at the same moments when aurora was visible in the sky above Uppsala. This was the first instrumental confirmation that the aurora and Earth's magnetic field were directly connected, establishing on a measurable, quantitative basis what Halley had proposed as a hypothesis. Benjamin Franklin added his voice to the scientific discussion in 1779, suggesting that the northern lights might be related to electrical phenomena, a partial insight that was ahead of its time in pointing toward the later understanding of charged particles as the aurora's cause, even though the specific mechanism Franklin imagined was not the one that science would eventually confirm. The most dramatic single event in the history of aurora science occurred on September 1st, 1859, when British astronomer Richard Carrington was conducting routine observations of sunspots when he witnessed an extraordinary brightening on the surface of the sun. A solar flare so intense that it was visible to the naked eye through his telescope's filtered projection. He recorded what he saw carefully, recognizing it as something unusual. What followed over the next 17 hours, the arrival of the associated CME and the geomagnetic storm it produced, established for the first time a direct observational connection between an event on the sun's surface and a subsequent geomagnetic disturbance at Earth. The modern understanding of the aurora's solar origin begins, in a meaningful sense, with Carrington's observation. The scientific figure who came closest to the correct explanation of the aurora before the space age was the Norwegian scientist Christian Birkeland, working in the late 19th and early 20th centuries. Birkeland proposed that electrons emitted by the sun were channeled to Earth's polar regions by the planet's magnetic field, the same basic mechanism that modern science has confirmed as correct. To support his theory, Birkeland constructed a remarkable laboratory demonstration called the Terrella, a small magnetized sphere placed in a vacuum chamber and bombarded with electrons. Aurora-like glowing rings formed around the magnetic poles of the sphere, providing a miniature but recognizable reproduction of the real phenomenon. The International Polar Year of 1882 to 1883 represented the first coordinated international scientific effort to study the aurora, with research stations established at multiple locations across the Arctic and subarctic regions simultaneously. The first aurora photograph was captured in 1892 by the German-American astronomer Martin Brendel, a long-exposure plate photograph that recorded the basic structure of an aurora arc. The space age transformed the science entirely. Spacecraft were able to directly observe the charged particles responsible for the aurora, measure the magnetic field interactions in real time, and confirm the mechanisms that earlier scientists had only been able to infer. The IMAGE satellite, launched in 2000, produced the first complete global images of the auroral oval, showing for the first time the full ring of aurora activity circling the magnetic pole from above. Before science existed to explain the northern lights, and long before any human being understood that the glow above the polar horizon had anything to do with particles from the sun or with the magnetic field of the Earth, people saw the aurora and responded to it the way people respond to beautiful and inexplicable things, with stories. Every culture that inhabited the high latitudes of the Northern Hemisphere, from the Norse peoples of Scandinavia to the indigenous peoples of North America, from the Inuit of the Arctic coast to the peoples of ancient Finland, looked up at the same shifting lights and wove them into the fabric of their understanding of the world. The stories they told were different in almost every detail, but the wonder that prompted them was universal and identical. In Norse mythology, the tradition of the Scandinavian and Icelandic Norse peoples, whose stories have been preserved in the Eddas and sagas, the Northern Lights were connected to two of the most visually powerful images in the mythological imagination. One tradition held that the aurora was the Bifrost Bridge, the shimmering, luminous pathway that connected the realm of human beings, Midgard, to the realm of the gods, Asgard. The Bifrost was described as burning and shimmering, trembling with light, and the aurora, seen against the dark Arctic sky in its most active and colorful form, would have been a natural visual inspiration for exactly such an image. A bridge of fire and light spanning the sky from horizon to horizon, present and then absent, changing and alive. A second Norse tradition connected the lights to the Valkyries, the warrior women of Norse mythology who rode through the skies above battlefields, choosing which warriors would die in combat and carrying the fallen to Valhalla. According to this tradition, the Northern Lights were the reflections of the Valkyries' armor and shields as they rode across the sky, their polished metal catching and reflecting some divine light and sending it rippling across the darkness. The image captures something true about the aurora's appearance, the way it can seem armored, structured, almost martial in its curtain and ray forms, moving with a kind of purposeful speed across the sky. The indigenous peoples of the Arctic developed their own distinct traditions around the aurora, each reflecting the specific cultural and spiritual frameworks of different communities. Among many Inuit communities, the lights were understood as the spirits of the dead, ancestors and others who had passed from life into another state of being, now moving and dancing in the sky above the living. The aurora was not frightening in this interpretation, but intimate, a reminder of those who had gone before, still present in some form, still visible on clear dark nights. Different Inuit communities held different specific beliefs about which spirits were present and what their movements in the sky might mean. But the fundamental connection between the aurora and the world of the deceased was widespread across Arctic cultures. The Cree people of North America called the Northern Lights the Dance of the Spirits, a name that captures both the movement and the spiritual significance that the lights carried in their cultural understanding. For the Cree, as for many other indigenous peoples of the subarctic, the aurora was not a meteorological curiosity or an astronomical phenomenon, but a living, spiritually significant presence in the sky, something that connected the visible world to the invisible world of spirits and meaning. Perhaps the most evocative of all aurora traditions comes from Finland, where the Northern Lights are called revontulet, a word that translates roughly as foxfires. The name comes from an old Finnish folk story of a great cosmic fox running across the fell landscapes of the far north, its tail sweeping the snowfields and sending sparks flying upward into the sky. The spraying sparks became the aurora, light scattered by the motion of something wild and fast and beautiful across the darkness. The image has a quality that resonates with the actual appearance of active aurora. The way light seems to spray and scatter and move across the sky in patterns that suggest motion, speed, something alive and in motion. In addition to these spiritual and mythological traditions, the aurora has occasionally been misinterpreted by observers who were seeing it for the first time, or seeing it at unusual low latitudes during great geomagnetic storms, and therefore encountering something for which they had no cultural context. Historical records contain accounts of aurora displays seen far from the polar regions during large events. Displays that were interpreted as fires on the horizon, as military conflagrations, as signs and portents. There are records of towns sending fire brigades toward what turned out to be aurora glow on the horizon. There are records of widespread public alarm during particularly vivid low-latitude aurora events. These misinterpretations are understandable. The aurora at low latitudes can appear as a deep red glow near the horizon, remarkably similar in appearance to a very large fire somewhere in the distance. What is striking about all of these traditions, the Norse bridge and the Valkyries, the Inuit ancestors dancing, the Cree spirits moving, the Finnish cosmic fox, is both their diversity and their underlying commonality. Different peoples with entirely different cosmologies and frameworks for understanding the world all recognized that the lights were something that demanded explanation, something that lay outside the ordinary and required a story to contain it. And all of these stories, in their different ways, place the aurora in a realm beyond the merely physical, a domain of gods, spirits, and powers larger than ordinary human life. Modern aurora tourism carries traces of this ancient impulse. People today travel great distances, from cities in Japan, China, North America, and Europe, to stand on a hillside in Norway or Iceland or Canada and watch the same lights that prompted the Bifrost story and the Foxfire legend. The physics is understood now. The electrons and the magnetic field and the atomic emission are known. And yet the response to standing beneath a full aurora display at 2 a.m. in a silent, cold, dark Arctic landscape is not primarily intellectual. It is the same response that every human culture that ever saw these lights has always had. A quiet, sustained sense of wonder at something beautiful and vast and not entirely comprehensible on any scale that the everyday mind is accustomed to. There is a particular quality to the story of how the aurora came to be scientifically understood. A quality of patient, difficult, occasionally brilliant work carried out by people who were, in many cases, working at the edges of what was technically possible for their era. The history of aurora science is not a smooth progression from ignorance to understanding. It is a series of insights separated by long gaps, of theories proposed before the tools existed to test them, of scientists who got important things right long before they could be proved right. And at the center of this history stands one figure whose work, largely dismissed during his lifetime and vindicated only after his death, represents one of the most compelling stories in the history of geophysical science. Christian Birkeland was a Norwegian physicist born in 1867. He came of age scientifically at a time when the aurora was recognized as a magnetic phenomenon. The work of Halley and Celsius and others had established that connection, but the underlying cause remained unknown. Birkeland developed a theory that the aurora was produced by electrons emitted by the sun and channeled to Earth's polar regions by the planet's magnetic field. This is, in its essential outline, the correct explanation, but the scientific tools and measurements needed to confirm it did not exist during his lifetime, and the mainstream scientific community of his era was skeptical. Birkeland was not a theorist who stayed in comfortable laboratories while proposing ideas about the Arctic sky. He organized a series of Norwegian polar expeditions between 1899 and 1903, establishing research stations at multiple locations across the Norwegian Arctic, specifically to observe and measure the aurora directly. These expeditions were conducted under conditions of considerable physical hardship. The Norwegian Arctic in winter is among the most demanding environments on Earth for sustained scientific fieldwork. Birkeland and his colleagues endured extreme cold, storms, and the physical and psychological challenges of polar darkness, all in service of gathering the magnetic field measurements and aurora observations that he hoped would support his theory. Back in the laboratory, Birkeland constructed what is perhaps the most elegant experimental demonstration in the history of aurora science: the terrella. The terrella was a small, magnetized sphere, representing Earth, placed inside a vacuum chamber. When the sphere was bombarded with a beam of electrons, representing the solar wind, glowing rings formed around the magnetic poles of the sphere, precisely where the aurora forms around Earth's magnetic poles. The demonstration was visually striking and conceptually clear. Here, in miniature and in the laboratory, was the aurora mechanism. Electrons from outside a magnetized sphere being guided to the poles and producing luminous rings. Birkeland presented this demonstration widely and used it to support his theory. Despite the elegance of his terrella and the rigor of his fieldwork, Birkeland's theory was rejected by the most influential geophysicist of the era, Sidney Chapman, a British scientist who developed a competing theory of the aurora that did not require electrons from the sun. The debate between the Birkeland and Chapman schools of thought persisted for decades. Birkeland himself died in 1917 in somewhat difficult personal circumstances before the question was resolved. He did not live to see his central insight vindicated. The vindication came in 1974, when the Triad satellite, one of the early scientific spacecraft of the space age, detected the electrical current sheets flowing along magnetic field lines between the magnetosphere and the ionosphere that Birkeland had predicted decades earlier. These structures are now called Birkeland currents in his honor. The satellite measurements confirmed that enormous sheets of electrical current do indeed flow along magnetic field lines between the outer magnetosphere and the polar ionosphere, exactly as Birkeland had proposed. His theory, dismissed during his lifetime, was essentially correct. The space age transformed aurora science in ways that no ground-based observation could have achieved. Satellites were able to leave the protective cocoon of Earth's atmosphere and directly sample the charged particles responsible for aurora, measure the magnetic field configurations in the magnetosphere and magnetotail, and observe the aurora from above rather than from below. The IMAGE satellite, launched by NASA in 2000, carried instruments capable of imaging the entire auroral oval simultaneously from high above the pole, producing the first complete global pictures of the ring of aurora activity surrounding the magnetic pole. For the first time, scientists could see the entire system at once, rather than inferring its global structure from local observations at different points. Several coordinated satellite missions have advanced the science further. The Themis mission, 5 satellites flying in coordinated orbits, was specifically designed to resolve the long-standing question of what triggers the sudden energy release in the magnetotail that produces aurora substorms. The mission found that substorm onset involves a complex interplay of processes, with magnetotail reconnection playing a central role. The ESA cluster mission, 4 satellites flying in a precise tetrahedral formation through the magnetosphere, has allowed the 3-dimensional structure of the magnetosphere and auroral acceleration regions to be measured for the first time. The Van Allen probes, operating from 2012 to 2019, provided detailed measurements of the radiation belts and the wave-particle interactions that energize aurora-producing electrons. On the ground, the aurora science infrastructure has grown significantly as well. The IceCat radar system in northern Scandinavia uses powerful beams of radio waves aimed into the ionosphere to measure electron density, temperature, and drift velocity in the auroral zone, providing high-resolution snapshots of the ionospheric processes associated with aurora. Networks of all-sky cameras, wide-angle cameras that photograph the entire visible sky simultaneously, distributed across the Arctic, provide continuous monitoring of aurora activity, building long-term statistical records and detecting substorm activity in real time. Sounding rockets launched directly through aurora displays have provided the most detailed in situ measurements of the electric fields and particle distributions within the aurora itself, filling in details of the acceleration process that neither ground-based nor orbital observations can fully capture. The aurora has become, in the language of modern science, a natural laboratory, a large-scale plasma physics experiment conducted by the solar system itself, accessible for study from the ground, from orbit, and from instruments placed directly within the phenomenon. One of the most quietly remarkable aspects of the aurora is that it is not a phenomenon unique to Earth. Wherever a planet has a magnetic field strong enough to interact with the solar wind, or an atmosphere dense enough to produce emissions when bombarded by charged particles, the conditions for aurora exist. The solar system, it turns out, is full of aurora, on gas giants, on rocky planets, on worlds whose conditions are very different from Earth's, each one a distinct expression of the same fundamental physical process, shaped by the particular magnetic field geometry and atmospheric chemistry of its host planet. Studying aurora beyond Earth has become an important part of both planetary science and aurora physics, because each planetary aurora is, in a sense, a different experiment in the same natural laboratory. Jupiter has the most powerful aurora in the solar system by a very large margin. Jupiter's magnetic field is approximately 20,000 times stronger than Earth's, and the planet itself is vastly larger. The result is an auroral oval that dwarfs Earth's in both size and energy output. Jupiter's aurora releases hundreds of times more energy than Earth's, driven by the enormous particle fluxes that Jupiter's powerful magnetic field can concentrate toward the poles. The aurora on Jupiter is primarily emitted in ultraviolet light rather than visible light, which means it is invisible to the human eye, but detectable and imageable by the ultraviolet instruments aboard the Hubble Space Telescope. Hubble has produced striking images of Jupiter's auroral rings, shimmering circles of ultraviolet emission surrounding the planet's poles, comparable in scale to the entire planet Earth. Jupiter's aurora has an additional and unusual energy source that has no equivalent at Earth. The Jovian moon Io is the most volcanically active body in the solar system. Its interior is kept molten by the tidal forces of Jupiter's gravity, and its volcanoes continuously eject sulfur dioxide and other materials into space. This volcanic material becomes ionized and trapped in Jupiter's powerful magnetic field, forming a dense plasma torus that circles the planet in the plane of Io's orbit. The particles from this Io plasma torus are continuously fed into Jupiter's magnetosphere and channeled to the poles, providing an aurora energy source that operates independently of the solar wind. Jupiter's aurora is, in part, powered by its own moon's volcanic activity, a chain of cause and effect that has no parallel at Earth. Saturn has its own aurora, also primarily ultraviolet, also imaged by the Hubble Space Telescope and by the Cassini spacecraft during its 13-year mission at Saturn. Saturn's aurora appears as a shimmering ring around the planet's south pole in Hubble images, a luminous oval of ultraviolet emission that expands and contracts with the level of solar wind activity, much as Earth's auroral oval does. Saturn's aurora is also influenced by material from its moon Enceladus, which ejects water vapor into space through geysers driven by subsurface liquid water, a Saturnian analog to the Io plasma torus, though less energetically significant. Mars presents a very different aurora environment. Unlike Earth, Jupiter, and Saturn, Mars does not have a global magnetic dipole field. Its global magnetic field essentially disappeared billions of years ago as the planet's core cooled and solidified. What remains are patches of magnetized crust, remnant magnetism from the ancient field, preserved in the oldest rocks of the Martian southern highlands. These patches of crustal magnetism create localized magnetic field structures above the surface, and in these regions, charged particles from the solar wind can be channeled toward the atmosphere in a way that produces aurora. The aurora on Mars is therefore patchy and localized rather than forming a continuous oval, a direct reflection of the patchwork nature of the remaining crustal magnetic field. It was first detected by the European Space Agency's Mars Express spacecraft. Venus presents yet another variation. Venus has no intrinsic magnetic field at all, neither a global dipole nor significant crustal remnants. Yet aurora-like phenomena have been observed in the Venusian atmosphere, produced by the direct interaction of the solar wind with the upper atmosphere, rather than by the channeling of particles along field lines. This Venusian aurora is more diffuse and less structured than Earth's, lacking the organization that a global magnetic field provides, but it represents a fundamentally different mode by which planetary aurora can be produced, one that does not require a magnetic field at all. Uranus and Neptune present the most geometrically unusual aurora environments in the solar system. Both planets have magnetic fields that are dramatically tilted relative to their rotation axes. Uranus's magnetic field is tilted by approximately 60 degrees from the rotation axis, and Neptune's by approximately 47 degrees. And in both cases, the magnetic field is also significantly offset from the planet's center. The result is an aurora that does not form a neat oval around the rotation poles, but instead wanders across the planet's surface in complex patterns as the planet rotates and the magnetic pole sweeps through different positions. These unusual geometries make the aurora on the ice giants considerably more complex and less predictable in structure than those on Earth, Jupiter, or Saturn. The aurora australis, the southern lights, is perhaps the most directly relevant aurora beyond the northern hemisphere for human observers. It occurs simultaneously with the aurora borealis at the conjugate point in the southern hemisphere, connected by the same magnetic field lines. The same energy release at the same moment, producing mirror image displays at both poles simultaneously. The southern lights are less commonly observed, not because they are less frequent or less spectacular than the northern lights, but because the southern hemisphere's auroral zone, the equivalent of the northern auroral oval, lies predominantly over open ocean and the Antarctic continent, both of which are far less accessible than the populated high-latitude regions of the northern world. From southern South America, the southern island of New Zealand, and Tasmania, brief glimpses of the aurora australis are possible during strong geomagnetic events. From Antarctica itself, the ideal location for southern lights observation, the displays are as spectacular as anything visible in the north, but accessible only to the researchers and expedition members who work there. There is a difference between knowing about the northern lights and seeing them, between understanding the physics of atomic emission and standing in a field at 2 a.m. in northern Norway, watching green curtains fold and ripple across the sky above you in complete silence. The experience of the aurora has a quality that scientific description can explain but cannot fully convey. A combination of the visual, the physical environment, the scale of what you are watching, and the quiet knowledge that something vast and mostly invisible is expressing itself in light above your head. Understanding what the experience is actually like, including its perceptual surprises and the ways it differs from the photographs that most people encounter first, is part of understanding the aurora as a whole. The first surprise that many first-time aurora observers encounter is the difference between what their eyes see and what cameras reveal. Photographs of the aurora, particularly the long-exposure digital images that have become ubiquitous on social media and in travel photography, show vivid, saturated greens, deep reds, swirling purples, and brilliant whites. These images are real. The aurora does emit those colors, but they represent the aurora as a camera with a multi-second exposure sees it, not necessarily as the human eye experiences it in real time. The reason for this difference is the biology of human vision. The human eye contains 2 types of photoreceptor cells. The cones, concentrated in the central part of the retina, are responsible for color vision, but they require a relatively high light level to function effectively. The rods, more numerous and distributed across the peripheral retina, are sensitive to low light levels and motion, but do not distinguish color. In dim conditions, such as a faint or moderate aurora, the rods dominate vision, The aurora is bright enough to see clearly, but not bright enough to fully activate the cone cells. As a result, a faint or even moderately bright aurora can appear grey or white to the naked eye. The green is there, measurable by instruments and capturable by a camera with a long exposure. But the eye does not have enough color-sensitive activation to perceive it as vividly green. As the aurora brightens, the cones begin to engage. A genuinely bright aurora, the kind associated with an active substorm or a significant geomagnetic storm, does show color to the naked eye. And in the most intense displays, the green can be vivid and unmistakable, with reds visible at the upper edges and occasionally blues and purples at the lower fringes. The brightest aurora events in history have reportedly been bright enough to cast shadows, vivid enough to make reading possible by their light alone. These extreme events are rare, associated with the most powerful geomagnetic storms, but they have been documented by observers across many centuries. The sounds of the aurora present a separate and scientifically unresolved dimension of the experience. Observers in very quiet Arctic environments, away from any wind, machinery, human activity, or animal noise, have for centuries reported hearing faint sounds during particularly intense aurora displays. Descriptions include soft crackling, hissing, swishing, or clapping sounds. Sounds at a low volume, but distinct enough to be noticed in a completely silent environment. These reports have been collected from across the Arctic and subarctic world, from different cultures and time periods, suggesting they are not simply misperceptions or fabrications. The scientific explanation remains debated. One proposed mechanism involves electrophonic effects, the rapidly changing electric and magnetic fields associated with aurora events interacting with conducting materials near the ground to produce faint mechanical or acoustic vibrations. Whether this mechanism fully explains the observations is still under investigation. The view of the aurora from the International Space Station represents a fundamentally different perspective, one that inverts the usual relationship between observer and phenomenon. From the ground, the aurora is above you. You look up into it, and it occupies a portion of the sky with the stars visible beyond and above it. From the ISS, orbiting at an altitude of approximately 400 kilometers, above the lower aurora, but potentially within or above the upper portions of intense displays, astronauts look down into the aurora. They see it as a thin, shimmering layer of color draped across the dark surface of Earth far below, with the stars visible above it in the blackness of space. It is a perspective that reveals the aurora's true nature as an atmospheric phenomenon, a thin, luminous shell embedded in the upper atmosphere, rather than a display projected on the dome of the sky. The optical illusion of aurora proximity is another perceptual phenomenon worth noting. Observers standing outside in a dark Arctic landscape, watching an aurora display, commonly report that the lights appear to be very close, just above the trees on the nearby ridge, or only a kilometer or two away. This illusion arises because the dark, featureless night sky provides no depth cues, no way for the visual system to calibrate distance. Without reference objects at known distances, the brain places the aurora at a subjectively comfortable distance, which feels close. In reality, the lower boundary of the aurora is approximately 80 to 100 kilometers above the surface. The curtain that appears to be just above the tree line is actually at an altitude where the International Space Station orbits. The trees are irrelevant to the scale involved. Modern technology has transformed the practical experience of aurora hunting. Smartphone applications connected to real-time satellite data provide continuous updates on solar wind conditions and KP index values, translating space weather data into simple forecasts of aurora visibility probability at specific locations. Dedicated webcams in popular aurora locations in Norway, Iceland, and Canada stream live sky views online, allowing people worldwide to watch aurora events unfold in real time from their own homes. When combined with travel to appropriate latitudes and a willingness to spend time outside in cold, dark conditions, waiting for the sky to perform, these tools have made experiencing the aurora more accessible than at any previous point in history. There is a paradox at the heart of the Northern Lights that is worth sitting with for a moment. The same phenomenon that draws people north to stand in frozen fields and watch the sky in wonder. The same shifting green curtains and red-edged rays that have inspired mythology and art and centuries of scientific curiosity is also the visible expression of a space weather event with the potential to disrupt the technological infrastructure that modern civilization depends on. The beauty and the practical consequence arise from the same physical process. The aurora glowing above the horizon is a sign that the magnetosphere is active, that electrical currents are flowing through the upper atmosphere, that the relationship between the Sun and Earth is being expressed with particular energy at this moment. And that energy does not stay in the upper atmosphere. It interacts with the conducting materials on and near Earth's surface in ways that, at sufficient intensity, can cause serious problems for the systems that keep lights on, communications working, and navigation accurate. The primary mechanism by which geomagnetic storms affect ground-level infrastructure is the induction of electrical currents in long conductors. When Earth's magnetic field changes rapidly during a geomagnetic storm, driven by the variations in the currents flowing through the ionosphere overhead, these changing magnetic fields induce electrical voltages in any long conducting structure lying on or near Earth's surface. Power transmission lines, railroad tracks, oil and gas pipelines, and the grounding systems of electrical substations all qualify as such conductors. The induced currents, called geomagnetically induced currents, or GICs, can flow through power grids in ways they were not designed to handle, saturating the cores of large power transformers and causing them to overheat, draw excessive reactive power, and in severe cases, sustain physical damage that requires months to repair. The event that most clearly demonstrated this vulnerability in the modern era was the geomagnetic storm of March 1989. On the evening of March 13th, a powerful CME, the product of solar activity several days earlier, struck Earth's magnetosphere. The resulting geomagnetic storm was classified at the most extreme level on the G scale. In the Canadian province of Quebec, the Hydro-Quebec electrical transmission system experienced a rapid series of relay trips as geomagnetically induced currents overwhelmed the protective systems designed to keep the grid stable. Within approximately 90 seconds, The entire provincial grid had collapsed. 6 million people in Quebec lost electrical power. The outage lasted up to 9 hours for many customers. Aluminum smelters, which require uninterrupted power for their industrial processes, suffered equipment damage that took weeks to repair. Across the northeastern United States, several high-voltage transformers were damaged, though a full grid collapse was narrowly avoided. That 1989 storm, significant as it was, occurred at a time when Earth's power grid was far less interconnected and electronically sophisticated than it is today. The scenario that motivates the most serious concern among space weather researchers and grid engineers is a repeat of the Carrington event of 1859, the most powerful geomagnetic storm in the instrumental record. Studies conducted by the National Academy of Sciences and other research bodies have examined what a Carrington-scale event would mean for the modern power grid. Their conclusions are sobering. A geomagnetic storm of that magnitude, striking today's interconnected global grid, could cause widespread damage to the large, high-voltage transformers that form the backbone of electrical transmission systems. These transformers are custom-built, weigh hundreds of tons, and take 1 to 2 years to manufacture and replace under normal industrial conditions. Replacing large numbers of them simultaneously, following a global geomagnetic disaster, could take years, leaving significant portions of affected regions without power for extended periods. Some studies have suggested that damage costs could reach into the trillions of dollars. Beyond the power grid, geomagnetic storms affect a range of other modern systems in ways that range from minor to operationally significant. Satellites in low Earth orbit are affected by the expansion of the upper atmosphere caused by aurora-related heating. The thermosphere swells outward as it absorbs the energy deposited by incoming particles, increasing the atmospheric drag experienced by satellites at orbital altitudes of a few hundred kilometers. This increased drag causes orbital decay to accelerate. Satellites lose altitude more quickly than planned, requiring orbit-raising maneuvers that consume fuel and shorten operational lifetimes. During the solar maximum period of 2002 to 2003, the Gravity Recovery and Climate Experiment satellites, GRACE, experienced significant unexpected orbital decay from geomagnetic storm effects on atmospheric density. The global positioning system, on which navigation, logistics, financial transactions, and an enormous range of other modern activities depend, is affected by geomagnetic storms through a different mechanism. GPS works by measuring the precise travel time of radio signals from satellites to ground receivers. These signals must pass through the ionosphere, the electrically charged upper atmosphere, and the ionosphere's refractive properties affect the signal travel time in ways that GPS receivers must correct for. Under normal conditions, the corrections are well characterized and the positioning errors are small. During geomagnetic storms and aurora events, the ionosphere becomes irregular and turbulent. The corrections become unreliable, and positioning errors can reach tens of meters in affected regions. For applications requiring centimeter-level precision, such as precision agriculture, land surveying, and some autonomous navigation systems, this degradation can be operationally significant. High-frequency radio communications, used by airlines for transoceanic flights, by military and emergency services and by amateur radio operators, rely on the ionosphere as a reflector that bounces signals over the horizon and across great distances. During aurora events, particularly in polar regions, the ionosphere can absorb HF signals rather than reflecting them, producing complete radio blackouts in the auroral zone. Airlines operating polar routes between North America and Asia, which pass through the auroral zone, can experience complete loss of HF communications during strong geomagnetic events. When this occurs, aircraft must reroute to lower latitudes, adding flight time and fuel consumption, or use alternative satellite communication systems. In response to these vulnerabilities, space weather forecasting has developed into an important applied science. The NOAA Space Weather Prediction Center issues geomagnetic storm watches, warnings, and alerts using the G-scale, analogous in concept to the system of watches and warnings used for terrestrial severe weather. Power grid operators receive advance notice of approaching CMEs and can take protective measures, such as reducing power transfers and increasing reactive power reserves to make the grid more resilient to GIC effects. Satellite operators can place satellites in safe mode during predicted intense periods to protect sensitive electronics. Airlines can reroute away from polar regions in advance of predicted HF radio blackouts, the aurora we can observe tonight, or on any clear night in the high-latitude regions of the world, is one moment in a phenomenon that has been occurring continuously for as long as Earth has had both a magnetic field and a solar wind to interact with it. That is a very long time. The geodynamo, the process within Earth's liquid outer core that generates the magnetic field, has been operating for at least 3.5 billion years. The Sun has been producing its solar wind for essentially its entire lifetime of approximately 4.5 billion years. The aurora, in some form, has been present in Earth's polar skies for most of the planet's history. Understanding the aurora in deep time, how it has varied, how the solar activity driving it has changed, and what the long record of aurora events reveals about the behavior of the Sun, is a dimension of aurora science that extends far beyond the timescale of human observation. The most direct historical record of aurora comes from written human observations. References that researchers interpret as aurora sightings appear in Chinese astronomical texts dating back perhaps 4,500 years. Ancient Greek, Babylonian, Roman, Japanese, Korean, and medieval European texts all contain descriptions of unusual lights in the sky that fit the pattern of major geomagnetic storm auroras visible at low latitudes. These historical records are imperfect. The descriptions were made by people who did not understand what they were seeing and used the vocabulary and interpretive frameworks available to them. But they preserve information about major aurora events across many centuries. Researchers studying these historical records have been able to identify specific events, estimate their intensity based on the range of latitudes from which they were observed, and place them in the context of the solar cycle. One of the most important insights from these historical records is the reality of long-term variability in solar activity. The Maunder minimum, a period lasting from approximately 1645 to 1715, is one of the most striking features in the aurora historical record. During this period, the sun was almost completely free of sunspots. The dark, magnetically active regions on the sun's surface that are the most easily observed indicator of solar magnetic activity. Sunspot observations from this period, preserved in European astronomical records, show that sunspots essentially disappeared for several decades. And in parallel, the historical record of aurora sightings shows a dramatic decline. Aurora events that had been relatively frequent before the Maunder minimum became rare. The handful of aurora events that were reported during the minimum were typically minor, confined to high latitudes, and much less spectacular than the events documented in the preceding and following periods. The correlation between the absence of sunspots and the dramatic reduction in aurora activity provided some of the earliest evidence that the aurora was directly connected to solar magnetic activity, that a quiet sun meant a quiet aurora. The Dalton minimum, a less severe but still significant period of reduced solar activity lasting from approximately 1790 to 1830, shows a similar, if less dramatic, pattern. Sunspot numbers were below normal, and aurora sightings were less frequent than in surrounding periods of more typical solar activity. The Dalton minimum was also associated with somewhat cooler average temperatures in parts of the northern hemisphere, a connection that researchers have studied as part of the broader question of how solar activity variations might influence Earth's climate. Though the relationship between solar variability and climate is considerably more complex than the aurora-solar activity connection. Beyond written historical records, the solar activity that drives aurora has left its mark in the physical structure of the natural world, in the annual layers of glacial ice and the growth rings of trees. High-energy particles from the sun, particularly during large solar flares, produce radioactive isotopes in the upper atmosphere, most notably carbon-14 and beryllium-10. These isotopes are produced more abundantly during periods of high solar activity and less abundantly during quiet periods. Carbon-14 is incorporated into the organic matter of living trees through photosynthesis, and when the tree grows a new ring each year, the carbon-14 concentration in that ring reflects the solar activity level of that particular year. Beryllium-10 is deposited in snow and eventually preserved in glacial ice. By measuring the concentrations of these isotopes in precisely dated tree rings and ice core layers, researchers can reconstruct the history of solar activity going back thousands of years, far beyond the period covered by written observations. These isotope records have revealed that solar activity varies not just on the 11-year sunspot cycle, but on longer timescales as well, including the centuries-long grand minima like the Maunder and Dalton minima, and corresponding grand maxima when solar activity was elevated for extended periods. The 20th century and the early 21st century have been a period of relatively high solar activity by historical standards, sometimes called the modern grand maximum, though recent data suggest that this period of elevated activity may be ending, with solar cycles becoming somewhat less intense. How aurora frequency and intensity will change in response to these longer-term solar variations is a question of ongoing research. Earth's magnetic field itself has been changing over time in ways that affect the aurora. The magnetic North Pole, around which the auroral oval is centered, has been drifting significantly in recent decades, moving from the Canadian Arctic towards Siberia at a rate of approximately 50 kilometers per year. This drift means that the geographic distribution of aurora viewing, which locations experience the most frequent and intense aurora, is gradually changing. Locations that have historically been within the auroral oval may find themselves less ideally positioned in future decades, while other locations may become better positioned. Over centuries and millennia, the change in the magnetic pole's position will shift the optimal aurora viewing geography substantially. The long-term weakening of Earth's overall magnetic field, which has decreased in average intensity by approximately 10% over the past century and a half, is also relevant to the aurora's future. A weaker magnetic field is less effective at deflecting the solar wind, meaning that for the same solar wind conditions, a weaker field allows more energy to enter the magnetosphere. In principle, this suggests that aurora could become more extensive at lower latitudes over time if the field continues to weaken, though the relationship is complex and other factors also influence aurora distribution. At some point in the geological future, Earth's magnetic field will undergo a polarity reversal, as it has done many times in its history, during which the auroral ovals will be disrupted and the pattern of aurora activity will be very different from what it is today. This last section of tonight's journey asks only that we rest in the quiet weight of what has been described, in the remarkable chain of events and scales and physical processes that converge to produce something as simply beautiful as the northern lights. Consider the journey of the electrons themselves. They were produced at the sun, expelled from the solar corona as part of the continuous solar wind, or launched more energetically in a solar flare or coronal mass ejection. They crossed 150 million kilometers of interplanetary space at speeds of hundreds of kilometers per second, carrying the sun's magnetic field with them. They encountered Earth's magnetosphere, were deflected, stored, accelerated. They traveled down magnetic field lines from the outer magnetosphere to the polar upper atmosphere, moving at approximately 70 kilometers per second, fast enough to cross the distance between Earth and the Moon in about 5.5 seconds. And at the end of this journey of days and millions of kilometers, their energy was transferred to an oxygen atom at an altitude of 100 kilometers above the Arctic tundra, and that atom released a photon of green light that traveled downward through the atmosphere to reach the eye of a person standing outside, looking up. That is the Northern Lights, a chain of physical events connecting the sun to a human eye, spanning the solar system in process, expressed in a photon of green light. Earth's magnetic field is invisible in daily life. We navigate by it through compass needles and satellite systems, but we do not see it or feel it. In the aurora, it becomes visible, traced in light by the electrons following its lines of force from the magnetosphere to the atmosphere. The magnetic field that protects Earth from harmful solar radiation is the same structure that enables the aurora. Protection and beauty arise from the same source. The lights in the sky are evidence that the shield is working. The aurora borealis and aurora australis occur simultaneously at conjugate points in the northern and southern hemispheres, connected by the same magnetic field lines. When the northern lights are active above Norway tonight, the southern lights are active above Antarctica at the same moment, mirror images of each other, the same energy release producing light at both ends of the same field lines at once. The physical symmetry of the phenomenon, the elegant pairing of northern and southern displays separated by 25,000 kilometers, but connected by the invisible geometry of the magnetic field, is one of those facts that rewards quiet reflection. Every color in the northern lights corresponds to a specific atomic process, a specific atom at a specific altitude, releasing a specific quantum of energy as a specific wavelength of light. The green is not simply green. It is a wavelength of 557 nanometers, produced by an oxygen atom at approximately 100 kilometers altitude that was excited by an electron from the magnetosphere and remained in its excited state for approximately 1 second before releasing its photon. The red is a wavelength of 630 nanometers produced by an oxygen atom at 200 kilometers or above, which remained in its excited state for up to 2 minutes before emitting. Behind the gentle, shifting beauty of the aurora lies a precision of atomic physics, a quantum mechanical exactness in which every color is a specific number, every transition a specific energy, every photon a specific message from a specific atom. The tradition of human wonder before the aurora is very long. Ancient Chinese astronomers recorded unusual lights in the northern sky 4,000 years ago. Greek philosophers wrote about flames and chasms in the sky. Norse storytellers saw the Bifrost Bridge and the Valkyries riding. Finnish poets imagined a cosmic fox sweeping fire across the heavens with its tail. Inuit communities saw their ancestors dancing. People have been looking up at the same lights and being moved by them for as long as human beings have inhabited the high latitudes of this world, and the experience of being moved by them has not diminished with scientific understanding. Knowing that the green light comes from oxygen atoms at 100 kilometers does not make the green less beautiful. Knowing that the curtains are shaped by magnetic field lines does not make the curtains less graceful. Understanding the aurora adds a layer of meaning to the experience, rather than removing the wonder. Some of the electrons that will produce tonight's aurora, if conditions are favorable somewhere above the Arctic, may already be traveling through space at this moment. They left the sun some time ago, crossed the solar system, and are following magnetic field lines toward the polar atmosphere, where their energy will become light. The lights that have been seen by human beings for thousands of years will continue to appear in the polar sky, produced by the same process, shaped by the same magnetic field, for as long as the sun produces its solar wind and Earth retains its magnetic field, which is to say, for a very long time indeed. Rest well. Somewhere above the Arctic tonight, if the sky is clear and the solar wind is favorable, the lights may be turning.